Okay, I think it has started recording. So let's start today's class. So we did not take last week's one class, we had a longish break therefore. So last Thursday we met, and Monday we did not meet. And let's continue from where we left. In fact, I'm not going to continue from where we left. So I told you that I would do chapter 2 of Lang, and which is what we have been doing. In the last 4 classes, we did initial parts of chapter 2 of Lang's book. So today I will go to chapter 1 and start from the scratch. So even if some of you have told me that you are finding the course a bit difficult, but I have told you that the course is a little bit advanced and maybe a bit difficult. But even if the first 4 classes you found difficult, start paying attention from scratch today, because we are not assuming whatever we have done in the last 4 classes. Okay, it'll come back later, but not for today, not in the next few classes. So let me start sharing the screen. Yeah, sharing the screen, and today's lecture 5. Okay, I hope you can see my slides. Someone can just confirm. One of you please confirm you can see the slides.
Yes, yes.
Okay, so let's start then. Yeah. So as I said, lecture 5 today, we are going to chapter 1 of Lang. Up to now in the last 4 classes, we were in chapter 2 of Lang. Chapter 2 has many other things, but I wanted to push it further, but I thought that some of the things that in chapter 1 are going to be used a little bit. So I thought, okay, this is a good time to come to chapter 1. So that's what we are doing today. So the key word today is integral closure. So we will define what it means to say that an element is integral. Okay, so you have already seen algebraic numbers, and we want to talk about algebraic integers. So more generally, we will start with some commutative algebra, and we will define an integral element, and we'll discuss some of its properties and prove some theorems, and we'll stop there. Yeah. So I will cover the basic notions about integrality. So let's start. So the last 4 classes, as I said at the beginning, we discussed the complete non-Archimedean fields. In order not to forget, let us just recall some things that we have done, though we are not going to use any of this today. So we saw results such as I always like the name theorems. So some names that we have seen: Artin-Vapels on absolute values, Hensel's lemma, Krasner's lemma, and in fact we saw 2 versions of Hensel, one in one class and another in another class. The second version we proved under the assumption that the valuation is discrete, though I did tell you that you don't need that assumption. It only made the proof easier. It is true for any complete non-Archimedean field. So these are the things that we have done. And then in the very last class, in lecture 4, we proved a compactness result. We proved that the ring of integers of a complete non-Archimedean field with a discrete valuation, O, we called it. It's compact. This was under a certain assumption that O by P is finite. Also, its units of that ring, that also is compact under the same assumption. And finally, we computed, this was the last slide of lecture 4. If K is a p-adic field we mean a discrete valuation ring and quotient field of that. We computed this index. So K star is a non-zero elements of your field, and K star power n is the nth powers, and then this index is finite, and we computed this index under this assumption that O by P is finite. Okay, then we computed this index, and I said this is a nice proof due to Emil Artin. It's there in Lang, and that's what we have done. So today we will move to chapter 1 of Lang. The first topic is integrality. So let's start. Yeah. Feel free to interrupt, ask questions if you want. I like anyway discussing. Okay, we don't have to just go through the slides. Whenever you feel like talking, just start talking. Talk a bit louder, only then it will be clearer to me. So the first topic is integrality. So beginning note, this is there in Lang's introduction that whenever he uses the word ring, what he means is an integral domain. Okay, so a ring for him is an integral domain. It is always commutative. It always has one, the identity element, multiplicative identity. Okay, so for Lang and therefore for us, a ring is a commutative integral domain with unity, with the multiplicative identity. Okay. Now A is a ring, so that means a commutative integral domain with 1, and L is a field containing A. Okay, this is your setup. You have a ring and a field containing A. L could be the quotient field itself, or it could be an extension of the quotient field. Okay, so L is a field containing A, and you take an element from L and you want to define integrality over A. So you take an element x in L and you say that x is integral over A. Integral over A if it satisfies a polynomial. So you know algebraic number, right? If it satisfies a polynomial with coefficients in the ground field, that's an algebraic number. Now we have integrality over A if it satisfies a polynomial where these coefficients are in A. AI are in A and n is greater than or equal to 1. So a non-trivial polynomial. And so if x satisfies a polynomial, monic polynomial, right? Monic polynomial, the leading coefficient is 1. So if it satisfies a monic polynomial with coefficients from a non-trivial polynomial, then you say it's integral. I hope this definition is clear. So if x is integral over a, then consider the following a module. Okay, so consider the module generated by, suppose x is integral over a and it satisfies this particular polynomial. Therefore, the leading degree is n, and I'm going to take the a module generated by 1x up to x power n minus 1. Okay, so the module generated by, where is this? This is contained in L, right? 1x etc. are contained in L. So what is the module generated by this? It is a plus ax plus etc. ax power n minus 1. So it's contained in L. So it's a module contained in L. And of course it's finitely generated. I'm giving you n generators. So you can consider this finitely generated module. And you observe that x times m is contained in m. That's clear, no? Because if you take anything here and multiply by x, so x times x is x square, which is already there, and x times x power n minus 1 is x power n. But x power n is also here because x power n is minus of this, and that is there in this module. So x times any element of this module is already there in that module. So xm is contained in m. So what we have just observed is if x is integral over a, then there is a finitely generated non-zero module, contained in L with this property that x takes that to itself. And we want to say that the converse is true. Conversely, suppose x is some element in L, this field containing A, such that there is a finitely generated non-zero module M, a module M contained in L, a module contained in L, such that this property is true. Xm is contained in M. This is what we proved earlier, no? If x is integral, then we proved there is such a module. That was obvious. Now suppose there is such a module with this property, xm is contained in M, finitely generated non-zero. We want to show that x is integral. That's also easy. So what you do is, we claim that x is integral. So it is given to be finitely generated, contained in L. Let there be, generators. Call it y1, y2, etc., yn. What is given to you? Xm is contained in M. Therefore, you will get a system of linear equations, right? X times y1 you can write in terms of this. X times y2 you can write as a linear combination of this, etc. So you get this system of equations where these A are A12, A11, A12, etc. are from where? It is from A because it's an A module. Okay. So x times y1 is a linear combination with coefficients from a. X times y2 is similarly this. Now so aij's are in a. Now can you see that x satisfies a monic polynomial in ax? That's what we wanted to show. We wanted to show that x is integral over a. Can you finish the proof?
Sir, I've seen the proof earlier, so should I still say?
That's okay. That's fine. Yeah. Go ahead.
Yeah, so you write it as a linear system in y1, y2, yn.
Yeah. And you will get a
And then you look at the determinant of that.
Yeah.
That must be 0.
Why that must be 0?
Because it is a... I don't know, maybe because we are taking a minimal generating set.
Yeah, so if that is 0, then that determinant polynomial, when you expand, that's a monic polynomial because its diagonal elements are x minus a1, 1, etc. Therefore, you're done. So only a small question is, you know in linear algebra that if you have such a system and if it has a non-trivial solution, right? This is a non-trivial solution, therefore the determinant has to be 0, right? If you have ax equal to b and if x is ax equal to 0, homogeneous system, and if x is a non-trivial vector, then determinant of a has to be 0, because otherwise you can multiply by a inverse and you will get x equal to 0. But here that is linear algebra is done over a field, whereas a is a ring. But the same idea will still work, but here you don't have to bother. So this is the only last remark. So name the polynomial. You have already named. It's a determinant polynomial. And the only notice that usual linear algebra is fine here because we are working inside a field L. AIIs are in A, but A is contained in L. So it is usual linear algebra only because we are always working inside a field L. Therefore, the other way is also true. Okay. So so this is so simple but very powerful. We are going to use it again and again and again. So an element is integral. An element from L is integral over A if and only if there is a module M which is finitely generated and non-zero as an A module such that Xm is contained in M. That's what we have proved. If and only if. Okay. Now suppose K is the quotient field. Yeah.
So what was L in the earlier thing? Like, can you go to the first slide?
L is any field containing your ring A.
Any field?
Any field containing A, then you will define an element there to be integral over A. So typically, you can take the quotient field of A and any field containing K. So that's how it will come, right?
Yeah.
But this is all that you need, any field containing A. And all these things are inside A. This module is inside L. I mean, all these things are inside L. This module is inside L. And this M is contained in L. And this linear algebra is being done in L, so everything is okay. It's usual linear algebra. Now suppose we call K to be the quotient field of A. Why there is a quotient field? Because A is a domain. Though I call it a ring, it's a domain. So quotient field is there. Okay. Now let X and L be algebraic over K. This means it satisfies a polynomial with coefficients in K. So an x power n plus etc. plus a naught equal to 0, where these ai's are in K because it's just algebraic. AIs are in AIs are in K, but it's a quotient field, right? So you can clear the denominators and assume that AIs are in A, but monic is not there. It's a monic if you have a monic polynomial with coefficients in K, or if you have any polynomial with coefficients in K, each of the an minus 1 you can write as bn minus 1 by cn minus 1 and clear the denominators, you will get a polynomial like this. So you can assume that the coefficients are in A with an not equal to 0. Right, the highest, the leading term will have some coefficient an. Okay, so multiply this polynomial, this equation throughout by an power n minus 1. What will happen? If you multiply by an power n minus 1, you get an power n x power n plus dot 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 a naught an power n minus 1 equal to 0. Now this element an times x is satisfying a polynomial, actually a monic polynomial with coefficients in A. So what is the conclusion? If x is any element which is algebraic, then there is a number, non-zero number with which you can multiply so that that becomes integral. So anx in L, why is anx in L? because an is in A and A is contained in L. So an is in L and x is in L. So an times x is in L. And this is integral over A because it satisfies a monic polynomial with coefficients in A. That is a definition of integrality. Okay. So it's integral
Sir?
over A. Yeah.
Sir, can you repeat, sir? Why a and x belongs to L?
Because an is from where? An is from where?
An is satisfy the polynomial.
True, but it is also from which set? Here, AIs are in A.
Yes, sir, clear, sir.
So an is in A, and our starting assumption is that L is containing A. So ANs are in A, therefore ANs are in L. Agree?
Yes, sir.
Okay. So AN is in L in particular, and X is from L, no? X
Yes,
is
sir.
L. Therefore, the product is in L. L is a field. Agree?
Yes, sir.
Okay.
Yes.
Yeah, ANX is in L. And this is integral over A, you agree? Because it satisfies a monic polynomial, no? This is like y power n plus something equal to 0, where y has coefficient 1. Okay, so it's a monic polynomial over, so it satisfies a monic polynomial over A. So what we have shown is, if you have any algebraic number, you can multiply it suitably with an element of the ring, and you can make it integral. So basically this is like clearing your denominator. Suppose you take a rational number, by clearing the denominator you can get an integer. This is basically that, right? If you have 3 by 4, you multiply by 4, you get 3. So you can suitably multiply so that you will get integrality. Okay, so this is easy observation. Let's continue. Suppose B is a ring containing A. So A is the ring that you started with, and B is a ring containing A. Then you say that B is integral over A. So you have to recall, your field theory, you have the definition of a number being, an element being algebraic, and the very next definition is a field extension being algebraic. You say that L over K is algebraic if every element of A is, or L is algebraic over K. Similarly, B is integral over A if every element of B is integral over A. That's a definition. Okay. So if B is a ring containing A, B is integral over A if every element of B is integral over A. If B is integral over A, and suppose B is finitely generated as an A algebra. So what does that mean? Finitely generated as an A algebra means there are some elements of finitely many elements of B, so that B is isomorphic to the polynomial ring A in that polynomial expressions with coefficients in A in those variables, in those elements. So B is integral over A, meaning there exists some x1, x2, etc. xn in B such that polynomial expressions in those xi's with coefficients in A. So A bracket x1, x2, etc. xn. So B is isomorphic to that. So that is finitely generated as an A algebra. So suppose B is integral over A and it is finitely generated. B contains A, so B is an A algebra. And suppose it is finitely generated as an A algebra, then we are claiming, because of the integrality, this is an important result. It's easy but important, that it is finitely generated as an A module. Okay, you see the difference, no? For example, polynomials in one variable over a field, let us say, k of x, k bracket x, that is finitely generated as an A algebra. In fact, it's singly generated. The variable x generates it, but it's not generated as a vector space, right? Because vector space basis will be 1x, x square, etc. up to infinity. So finitely generated as an A module is as linear combinations. The ring operation is not allowed. Multiplication is not allowed. Only scalar multiplication and addition. Okay, so this is an important result. If you have integrality from finite generation as an algebra, you can conclude finite generation as a module. So let's see the proof. So B is finitely generated as an A algebra means there exist elements in B x1, x2, etc. xn such that B is A bracket x1, x2, etc. xn. So this will have all polynomial expressions. So summation some multi-index x1 power I1, x2 power I2, etc., xn power in. All these things are there. All these things are the elements of this. So this is there, but this you can write as expressions in xn alone with coefficients in this polynomial ring. You agree? This is same as this, right? So you can take this as the variable and all the other things you can put as coefficients. Okay. So now xn is integral over a because all these things are integral, x1, x2, etc. xn, all these are integral over b. Any element of b is integral over a. In particular, xn is integral over a. So that means it satisfies a monic polynomial with coefficients in a. So if you take any ring containing a, then xn is integral over that ring also, no? Because coefficients are in the subring, so it will be in the bigger ring. Therefore, it's integral over this ring, a, x1, x2, etc., xn minus 1. So you have got an element which is integral over this, and from that you can conclude that B is finitely generated as a module over this ring. Why is that? Because if you have, this is the very first observation that we have done. If you have a ring A and if you have an element X which is integral over A, then A bracket X is finitely generated as a module, right? No, not A bracket X, yeah. Yes, A bracket X, because 1 X etc. X power n minus 1, if the polynomial satisfied by x has degree n, then 1 x etc. x power n minus 1 will generate the module A bracket x. So this is the bigger ring and there is just one element which is integral over this. Therefore, this ring is finitely generated as a module over up to xn minus 1. So B is finitely generated as an A bracket x1 etc. xn minus 1 module. Okay. Now by induction, so you can do this by induction. So by induction up to n minus 1, A bracket x1, x2, etc. xn minus 1, you can assume is a finitely generated A module. Why? Because it's a finitely generated A algebra, and by induction hypothesis, the result is true. So it is a finitely generated A module. So what do you have? You have B is a finitely generated module over something, and that something is a finitely generated A module. So can you conclude that B is a finitely generated A module? So B is finitely generated over some C and C is finitely generated over A. Can you conclude B is finitely generated over A? Yes or no?
Yes.
Yes, no, clearly, right? I mean, it's like vector spaces, right? If you have L over K over F, if K over F is generated by, I mean, has dimension n and the other has dimension m, then the dimension is mn. So here only spanning is required. So it is clearly generated. You can give an explicit generating set. So by transitivity, B is finitely generated as an A module, which is what we wanted to show. If B is integral over A and finitely generated as an A algebra, then it is finitely generated as an A module. So by induction, it is done. So B is finitely generated as an A module. In fact, we have proved the following. I'm not using B integral over A. What I am using is, if you have n elements of B which are integral over A, then A bracket x1 etc. xn is finitely generated as an A module. This is what I have proved. I'm using only this x1, x2, etc. xn. I'm not using any other element. Okay, so remember this. What we have proved is, if you have n elements from B, and if these n elements are known to be integral over A, then we have proved that A bracket x1, x2, etc. xn, this ring is finitely generated as an A module. And we are going to use this in the next slide. Next or next to next. Okay. So now you know that if L over K over F, if L over K is algebraic and K over F is algebraic, then L over F is algebraic. This is called transitivity in field theory. And similarly, you have transitivity for integrality. Suppose you have A is contained in B is contained in C, and B is integral over A and C is integral over B. What is my claim? The heading is transitivity. So what is my claim?
C is the integral over A.
P is integral over A. That's my claim. Okay, so pay very close attention. It's there's a crucial step in the proof. Okay, we are going to use the previous slide. So let x belongs to C. What do you have to show? An arbitrary element of C is integral over A. So take randomly one x in C. Okay, arbitrarily an x in C. We have to show that x is integral over A. That's what we have to show. So what is given to us is C is integral over B. Therefore, x satisfies a monic polynomial with coefficients bi's in B. This you know. Now bi's are in B. Now comes the crucial step. So this is the only thing that you have to remember in this proof. I'm going to form this ring B1. So B1 is the ring formed by A adjoining the coefficients of the monic polynomial satisfied by x, B0, etc., Bn minus 1. Okay, so you start with an arbitrary element x. So now you have fixed that x. X satisfies a certain polynomial. Look at the coefficients of that polynomial, adjoin that to A and form that ring. Call that B1. So what do you know about B1? What can you say about B1? So these bi's are from B, no? Bi's are from B, and you know that B is integral over A. So these bi's are integral over A. So from the last slide, what can you conclude about this ring? If the algebra generators are integral, then what can you conclude about this algebra?
Finitely generated as an A module.
As an A module, yes.
Yes.
So that's what we proved. So finitely generated as an A algebra is clear, but the crucial point is finitely generated as an A module. So that was non-trivial. Non-trivial in the sense there was something to be done. So we have proved in the last slide that B1 is finitely generated as an A module. So that Y is answered the previous slide. And now consider B1 and X attached. Consider B1X. This is finitely generated B1 module. Why? Same argument. Because X is integral over B1. Why is X integral over B1? By construction. Because X satisfies this polynomial and these are part of B1. So X is integral over B1. Therefore, by the same argument, B1 bracket X is finitely generated B1 module. Same argument. So this Y and this Y, the answer is the same. Okay. So now we are in a good situation. We have got B1 bracket X is a finitely generated B1 module, and sorry. So, oh, what happened when the phone rang? My screen disappeared. Okay, you can see, no? So B1 is a finitely generated A module. So B1 bracket X is a finitely generated B1 module, and B1 is a finitely generated A module. So exactly as in the last slide, what can you conclude? B1X over B1 and B1 over A. Both are finitely generated. So the conclusion is?
Sir, B1X is a finitely generated over A module.
Over A module. Excellent. So B1X is a finitely generated over A module. What do we have to show? We have to show that X is integral. And our first slide was integrality is equivalent to producing a finitely generated module M contained in L, of course, such that Xm is contained in M. So is it true that X times B1X is contained in B1X? Is this true? This is your M. B1X is your M, which is a finitely generated A module. And X times B1X is clearly contained in B1X. No, because of this. Because X power, in fact, 1X, etc., X power N minus 1. Yeah, so X times anything from here, X times that, you can use this and reduce it to that again. So this is clear from this equation. Agree? Therefore, you have got a finitely generated module M such that X times M is contained in X, and that M is an A module. This is the crucial point. It's an A module. So you have got an A module such that X times that is contained in that itself. And what is the conclusion? Therefore, X is integral over A. So you have proved transitivity. So it's a, it's an important proof. It's not obvious. It's not like, you take that polynomial and for coefficients you take another polynomial. There's this crucial step in the construction, and you are using that a finitely generated algebra is finitely generated as a module under integrality. Is this proof clear to all of you? These are basic algebra, but ingenious. There is one crucial step here. Can I go to the next slide?
Yes.
Yeah. So go through the slides after the class also carefully. So what we have shown is transitivity. Okay, if A is contained in B, B is contained in C, C is integral over B and B is integral over A, then C is integral over A. Now a very trivial remark, but very, very useful. Okay, so you can always look at my titles. The title is summarizing what is coming here. So this is called homomorphism. So under a homomorphism, how integrality behaves. Suppose A is contained in B and B is integral over A. Okay, now you take any homomorphism of B. I'm not bothered about what the image is. Okay, you could have called this sigma of B. That doesn't matter. Okay, sigma is a homomorphism from B to some other ring. Okay, which I don't even name. So sigma is a homomorphism on B. And then the claim is, so I'm going to claim, so what, okay, why don't you try to guess what should be my result, which will come here at the end of the slide. You have a homomorphism and X is integral. X is integral over, suppose B is integral over A, what should be my claim?
Oh, like, is the homomorphism fixing A? Then you can say that sigma of X is integral over A.
Yeah, good, very good. So that is certainly correct. So, but suppose it doesn't fix A, then also you can make a statement, no?
Integral over sigma of A.
Correct, correct, absolutely. So that's the statement. So if X and B satisfies this polynomial, because X is integral over A, it satisfies some polynomial where these AIs are in A, you apply sigma, it's a ring homomorphism. So you will get sigma X satisfies this polynomial. So conclusion is sigma X is integral over sigma of A. So that's an easy observation, okay? So therefore sigma of B is integral over sigma of A, as you have already guessed. So that's an easy observation. Now let's define what is called integral closure. So again, you remember your field theory. Once you define algebraicity and once you define transitivity of algebraic extensions, etc., you have the notion of an algebraic closure. Similarly, you have the notion of integral closure. So A is a ring contained in a field L. Let B be the set of elements of L which are integral over A. So you consider all possible elements of L which are known to be integral over A, which are integral over A. Okay, consider this collection. Then the claim is that collection is actually a ring. So what does this mean? What is the statement? So if you take two integral elements, their sum is also integral. If you take two integral elements, their product is also integral, etc. Everything for a ring is satisfied. Ring meaning integral domain. So everything is satisfied. Okay. So this is the claim. So this we have to prove. This is not obvious. No. If x and y are integral, then x satisfies a monic polynomial, y satisfies a monic polynomial. Now x plus y satisfying a monic polynomial is not all that obvious. Some work has to be done. And similarly for xy. So we will do that. Okay, so the claim is it's a ring, and that is called the integral closure of A in L. So is the definition clear? A is contained in L. All those elements in L which are integral over A, put that together. It happens to be a ring, and that ring is called the integral closure of A in L. That it is a ring we are yet to prove. We haven't proved. That's called the integral closure of A in L. So let's prove that. Okay, so suppose x and y are in B, so that means x and y are integral over A, and therefore we have this other criterion, right, using finitely generated modules with a property. So corresponding to x, there is a finitely generated non-zero module M, capital M, such that x times M is contained in M, and corresponding to y, there is a finitely generated non-zero module N contained in L such that x times N is contained in N. Okay, so this much you know. So there are finitely generated A modules M and N such that
you can just take Rx and Ry, no? R
you could have
bracket X.
yeah, that M, yeah, so in this direction that was your M. right? M is AX. A is my ring. So AX and A. Yeah, I have written M and N. Okay, because I'm directly appealing to that theorem that if and only if there is an M such that XM is contained in M, XN. That's my, that's a wording that I remember. That's all. This particular M turns out to be RA, AX. You're right. Okay. So there are finitely generated A modules M and N, AX and AY, such that X times M is contained in M and Y times N is contained in M. Now with M and N, you form this product. Now, in module theory, you take sum of modules. But do you take product of modules? No. No. But here I have this notation Mn, and this notation, the only word to use is a product. But can you make sense of this here? So suppose, I want to define a product. How will it be? Module is like an ideal, no? So how do you define product of ij? I and j are ideals. What is the definition of product ij? If I and j are
Like
ideals.
the ideal generated by small m into small n, where m and n will small I into small j, where small.
Correct. And that will be just finite linear combinations, no?
Right.
So finite linear combination. So summation ai bi, it's a sum is finite, and ai is from I, bi is from j, right? So similarly, let us write this down. So these are, so I haven't set finite, but this is finite summation mi ni, mi in m, ni in n. Does this make sense?
It makes sense because it's a ring over here. We are in a field actually. But one thing, like if you are taken Rx and Ry, then we can just take R of x comma y.
Yes, correct. Which is same as this. So here it makes sense, and you have answered because these are inside a field. So taking product makes sense because both are contained in L. So MINI makes sense, and you can take this. And then this is, of course, a module. Once the definition makes sense, of course, it makes sense because we are inside a field, and then it is a finitely generated module. You are right. So if it is AX and AY, then this will be a polynomial expression in X and this will be a polynomial expression in Y. So the product will be a polynomial expression in X and Y, and finite sum of that again will be a polynomial expression in X and Y. So this product is nothing but A bracket X comma Y, and that's a finitely generated A module such that it has the property that X plus Y times that is contained in that, and XY times that is contained in that. As I guess it was Manav. So as Manav said, if this was AXY, then it's obvious that X plus Y times AXY is contained in AXY. Similarly for XY. So because it is a finitely generated non-trivial module, you have proved that X plus Y is algebraic, X minus Y is algebraic, XY is algebraic, proving that this is a ring. Okay. So this is the proof that it's a ring. You could have proved directly also, but then it requires a bit more work and bit more computation. So Mills notes he proves it this way and that way, directly, without using this characterization. So one note which I saw in Mills online notes that this proof is actually due to Dedekind. So Dedekind is a name that will come often in this course, algebraic number theory. In fact, we are going to study what are called Dedekind domains. A certain kind of commutative ring is called a Dedekind ring or a Dedekind domain. So this is that Dedekind, Richard Dedekind, a German mathematician. So apparently this particular proof is due to him. Okay, so we are making slow progress. Now we have defined what is called an integral closure. So what is the integral closure? Integral closure of A in L is set of all those elements of L which are integral over A. Put that together. That is the integral closure. It is a ring. Now here is a result about the coefficients of the minimal polynomial of an integral element. So our notation A is a ring, K is its quotient field, and L is a finite separable extension of K. This is what you have. And suppose X is an element in L and assume that X is integral over A. So X is integral over A. X has a minimal polynomial, right? The smallest irreducible polynomial satisfied by X. And what should be my result given the title? Guess the result. X is integral over A. Just take a guess. I mean, you can be wrong. After all, I'm not asking a precise mathematical question. Just from
the minimal polynomial lies in AX.
the coefficients of
Polynomial lies in AX.
lies in
Lie in A.
lie in A. Yes. In plain English, coefficients of the minimal polynomial. No. Minimal polynomial of X. Yeah, okay, of course. I mean, I said asked you to guess something. That's what you guessed, but I don't think that's what we are going to show. What we are going to show is, see, where will be the coefficient?
Integral over A. Minimal polynomial coefficient integral over A.
Yes. So we are going to show that the coefficients of the minimal polynomial are integral over A. That much only we can conclude. Not that they are actually in A, they are integral over A. That's what we are claiming. So let's see the proof. So you take any isomorphism of L over K, right? Then what can you say? If you have any such thing, so that is what can you say about sigma of X? We have shown earlier that sigma of X is integral over sigma of A, but sigma is an isomorphism over K. So sigma of A is A. So the claim is sigma of X is integral over A. Sigma X is integral over sigma A, which is A. So sigma X is integral over A. Now what do you know about the coefficients of the minimal polynomial? Coefficients of the minimal polynomial will be a certain polynomial expressions in sigma X, right? As sigma varies. Right? The coefficients of the minimal polynomials are given by sums and products in certain ways. In fact, elementary symmetric functions in all the conjugates. So all the sigma x's. So coefficients of the minimal polynomial are nothing but elementary symmetric functions of sigma x, and these involve only sums and products. But we have already shown that integral closure is a ring. It's a ring. Therefore, the coefficients are in that ring. So integral elements form a ring. Therefore, the coefficients are integral. Agree? So integral closure is a ring is used here, and this under homomorphism how it behaves. Putting those two together, if you have an algebraic, if you have an integral element, you take its minimal polynomial, all its coefficients are automatically integral. In particular, two coefficients have very famous names. No, what are they? There are, if degree is n, there are n minus 1 many coefficients. It's monic, therefore n minus 1 many other coefficients. And there are two of them which have particular names, no? What are they? The constant coefficient, the last one, and the second coefficient, the coefficient of n minus 1 degree. These two have some names, no?
I don't know, but I'm just guessing maybe trace and determinant.
Trace and determinant usually in linear algebra and in field theory.
Sorry, your voice got cut off. Hello?
In field theory. In linear algebra, yes. Last one is trace and last one is determinant and minus of this one is trace.
Symmetric function. Linear algebra, I don't know of any name. I don't know.
No, you know a name. So there is trace in field theory also, no? What is trace?
Saying something.
Haven't you seen trace in field theory, in Galois theory? Trace is sum of all the Galois conjugates.
Yeah, okay.
Yeah, that is called trace. No, if you have an extension L over K, then you have any element X in L, you have its trace, no, which is an element of K. You haven't done this?
I don't remember the name exactly.
Okay.
Maybe
So sum of Galois conjugates is called trace. It is like the trace of matrix. It's a parallel here. And now can you guess the parallel name for the determinant? It's not called determinant here.
Multiplication of Galois conjugate.
Yes. So what is the word for that? See, in linear algebra, sum of eigenvalues is trace and product of eigenvalues is determinant. So similarly here, sum of Galois conjugates is called trace, but product of Galois conjugates is not called determinant. There's another word. So I have never taught that course, so I don't know exactly what is taught. And even if it is taught, maybe sometimes the concepts may be taught without the name. So I don't know whether you have seen it, but try to take a guess. As like trace, maybe similar time you might have heard one more word, no, which is multiplicative. Product of Galois conjugates. Okay, maybe you haven't seen that. It's called norm. Have you seen this notation? Norm of x, norm, N-O-R-M.
I don't think I've seen it. I don't.
Okay. So now the definition is clear. Norm of x by definition is product of its Galois conjugates. Trace of x by definition is sum of Galois conjugates. Okay, so in particular, so it's exactly like determinant. This is like the determinant and this is like the usual linear algebra trace. In the sense, this is sum of Galois conjugates. So this will be the constant term of the minimal polynomial. No, sorry. This will be the minus of the second term of the minimal polynomial, and this will be the constant term of the minimal polynomial. So in particular, each coefficient is integral. In particular, norm and trace are integral. You know the properties of trace and norm. No, now that I have defined it, trace is an additive homomorphism. Trace of x plus y is trace of x plus trace of y, because it is sum of Galois conjugates, and each sigma is a field morphism. It is multiplicative as well as additive. Because you are taking the sum, trace is additive. Similarly, norm will be multiplicative. Because
Norm is product or minus 1 power n times product or something.
no, just take product.
So not the constant term, right? It's like
Okay, so maybe I got confused. Not the constant term, maybe
minus 1 power n times
minus
or
1
minus 1
power
power
n
n minus
minus
1
1
times.
times the constant term. Minus 1 power n minus 1 times the constant term. Yeah, but norm is just the product. So minus 1 power n minus 1 times the norm is the constant term. Okay, and minus of trace is the second term. So what you need to remember for the future classes is norm is multiplicative. Norm is a multiplicative homomorphism. From where to where? From L star to K star. Any non-zero number has a norm. And norm is a multiplicative morphism from L star to K star, and trace is an additive morphism from L to K. Okay, so in particular, these are integral. Now let us come to, so you have algebraic closure and you have algebraically closed. What is the definition of a field being algebraically closed? Field is algebraically closed if
every monic equation has all its roots in.
Has all its roots there. So if anything is algebraic over it, it's already there. That's another way of putting it, right? If anything is algebraic over that field, that is already there in that field. That's same as saying all the roots are there. So similarly, a ring A is integrally closed in a field L if every element of L that is integral over A actually belongs to A. So integrally closed. Okay. So if every element of L which is integral over A, so what is such a set called? All elements of L which are integral over A is called, what was the name? Integral closure. So what we are saying is all those elements in the integral closure are actually in A. So A is certainly contained in A bar. Let's say A bar is the integral closure of A. A is clearly contained in A bar because you can take x minus A, the linear polynomial. Now if A bar equal to A, then you say that A is integrally closed. This is very parallel, no? K is algebraically closed if K is K bar, right? K is equal to its algebraic closure. Similarly, A is integrally closed in L if the integral closure of A in L coincides with A. If every element of L which is integral over A belongs to A, then A is integrally closed in a field L. Now suppose I say A is integrally closed. There is no field L mentioned. What should be the definition? Take a guess. Say that again.
In the quotient field, integrally
in
closed.
The quotient field, absolutely. So if we just say something is integrally closed and no field is mentioned, then that means it's integrally closed in its quotient field. So A is just said to be integrally closed if it is integrally closed in its quotient field. Okay, so the definitions are clear. So integrally closed in a field, meaning the integral closure in that field coincides with A. If we don't mention the field, then the field is the quotient field. Okay, so is Z integrally closed? Usual integers, is it integrally closed?
Yes.
Yes, because you have to check in Q and you take anything in Q A by B, and if A by B satisfies a monic polynomial with coefficients in Z, then you can check that it has to be an integer. So Z is integrally closed. Okay. So now we are going to prove a very important result. Okay, so I have done it slowly over many slides, and pay attention to all the titles of the slides. So because I would like you to remember this proof forever. It's a very important statement as well as a very nice proof, and you should remember this proof. Okay, so I have given nice titles just to remember in a nice way. Okay, so the result is about finite generation. So we come to an important finite generation statement. Notations are as before. A is a ring. A is a ring, and K is its quotient field, and L is an extension of K, which we are going to assume is finite separable. It's a finite extension and separable. Separable means what? Separable means what? Every element of L is separable over K, and an element is separable if its minimal polynomial has
No repeated roots.
no repeated roots, distinct roots. So this is the situation, and this you will see. This I'm going to use because you have characterizations of finite separable extensions. Maybe you haven't seen it, but I will state it and go ahead. It's from field theory. Okay, so this is the notation. A is a ring, K is its quotient field, and L is a finite separable extension of K. And we are going to prove a finite generation statement. We want to prove, so we have A contained in L, and we want to say that, so this is what we want to broadly say, but I'm not going to give the precise statement now. Precise statement will come from the proof. Okay, we want to say that the integral closure of A in L, which we have defined, all those elements of L which are integral over A, that is called the integral closure. So that is a ring. We have proved that that is a ring, right? We already proved that it is a ring. So that is a ring containing A. So let's call it B. So B contains A. Therefore, B can be treated as an A module. Now, can you guess what is this finite generation? What should be my statement?
It is generated as an A module.
Yes. So that is the result. Integral closure of A in L is finitely generated as an A module. Over A meaning as an A module. Because B contains A, B is a ring, A is a ring. B is a ring we have already proved. In particular, it turns out to be an A module, and as an A module, it is finitely generated. This is not true. In this generality, it is not true. We have to put some conditions on A. Right now, what is A? A is any integral domain commutative with unity. We need to put some conditions on A. Okay, so that will be my theorem. I will never state a theorem. I mean, I may state a theorem some other time. This theorem I am not stating, but you will see what the result is. So this is what we want to show, that the integral closure is finitely generated over A. I have to put two conditions on A. Let's put the first condition. So what does this mean? You have already explained as an A module. We will have to impose conditions on A in order to achieve this result. Let's put the first condition. I would like you to guess it. Finite generation, this word in commutative algebra should tell you about one name, one word. Reminds you of what in ring theory? I mean, again, a vague question. I don't know whether I'm conveying my question. I want a word and I would like you to say it. That's all. So give one or two words. I will pick the correct one.
Noetherian.
Yes. So who said this? Noetherian, is it?
Pradyumna.
Pradyumna. Good. So Noetherian. It reminds you of Noetherian because when you deal with Noetherian rings, you see this word finitely generated again and again. For example, one characterization of Noetherian ring is every ideal is finitely generated. You would also have seen Noetherian modules, etc. So finite generation anyway reminds you of Noetherian. So that is our first assumption. So I have changed my title Noetherian. So first of all, we assume that the ring A that we start with is Noetherian. We want to show that A is contained in L, and we want to show that the integral closure of A is finitely generated as an A module. That's my research. And I'm going to assume A is Noetherian. Okay, that condition is required, but that's not enough. I need one more assumption. We will do it later. That's one condition. Okay, we will need one more condition. So I'm stressing this so that you will remember finally that there is one more condition. We will need one more condition which we will add at the right time when we need it. Okay, so let us proceed assuming only Noetherianness. So first claim, it's enough to prove that. So what do we need to prove? We need to prove that the integral closure of A in L is finitely generated. So we want to prove that something is finitely generated, and I am going to say that the integral closure of A in L, we have to prove that this is finitely generated, and my claim is it is enough to show that this is contained in some finitely generated A module. Do you agree that this is enough? Can you finish the proof? If this is given, if this is proved, can you finish the proof? We are going to prove that the integral closure of A in L is contained in some finitely generated A module, one finitely generated A module. Is that enough to show that the left hand side is finitely generated? I'm saying it is, answer is yes. So can you give the proof?
Sir?
Yeah.
Actually, sir, A is a Noetherian.
Yeah, A is Noetherian as a ring.
Noetherian,
Yes.
and any module is finitely generated, then it is a Noetherian.
Yeah, as a module.
Yes, sir. Then every submodule of M is finitely generated.
Very good. Who is this? Is this Amanpreet?
No, sir. Nitesh, sir.
Nitesh. Okay. So Nitesh, very good. So A is Noetherian as a ring. So any finitely generated A module is a Noetherian module, and a Noetherian module, one characterization is every submodule is finitely generated. So integral closure of A in L we are considering as an A module, and it is a submodule of this module, and therefore that is finitely generated. Therefore the result is done. Okay, I hope others have followed. So this is enough. Why? Nitesh just gave the argument which is there in my slides. A finitely generated A module is Noetherian as A is Noetherian, and thus all its submodules are finitely generated. Okay, very good. So this is what we are going to prove. The integral closure of A in L. I am going to exhibit a finitely generated A module which contains the integral closure of A in L, and then we are done. Okay. Right now we are assuming Noetherian, and that is used already in this without loss of generality statement, and we need one more condition which will come later. Now I'm going to introduce, so we introduce a trace function. I'm going to introduce a bilinear form in terms of trace. What is a bilinear form in linear algebra? If you have a vector space, then what is the notion of a bilinear form on a vector space? Suppose you have a vector space over a field K.
A map
Linear
from
and
V
both
cross V.
variables individually.
Yes, so it is a map from V cross V to K. So x comma y going to B bracket x comma y, where B is your bilinear form, and it is linear in each variable. If you treat one variable as a constant, it is linear in the other. And do you know this notion of a bilinear form being non-degenerate? When do you say that a bilinear form is non-degenerate?
If for every x there exists a y such that v of xy is not equal to 0.
Correct. Who's answering this? See, I'm on this page, so I can't see the names. Who said this?
Pradyumna.
Pradyumna. Okay. So B of for what did you say? If what did you say once again? You please tell me.
For every x non-zero, we have
Yeah.
a y such that v of x comma y is non-zero.
Correct. For every non-zero x, there is a y such that B of x comma y is non-zero. Other way to say this is if B of xy is 0 for all non-zero y, then x is 0, contrapositive, right? So this is non-degenerate, and maybe I'm going to state a result which
And
I don't know.
same for the other variable also, right?
Same for the other way. You can state in terms of one of those.
No, but we need to state for both of them, right? That's for the definition to be complete. Unless it's a symmetric bilinear form or something.
Okay. So yeah, fine. Yeah, you need to state in terms of both. And yeah, so if it is symmetric, then you don't need to state in terms of both. Correct, you are right. Yeah. So the bilinear form that I have is symmetric. Okay, it's using trace. Yeah, correct. So you know the notion of non-degeneracy, and you are going to have some result from field theory. So now I'm a bit doubtful how much field theory you have done, since you haven't heard the word norm, etc. But we will see. Okay, otherwise I'll assume it and go ahead. So an important role in the proof. So this is what you have to remember about this proof, that already Noetherianness has automatically come. There is one more condition which will come. So you finally remember that there are two conditions imposed. And also remember that this bilinear form, this particular bilinear form plays an important role. Okay, so an important role is played by the so-called trace bilinear form, which is defined as, so L is an extension of K, finite separable extension, and therefore L you can think of as a vector space over K. And then if you take these two vectors, I am going to take the product of x and y, which is in L, and just take the trace. Trace is sum of the Galois conjugates. And this is linear in each variable is clear, no? If you have x1 and x2, then if you sum here, you will have x1 plus x2 comma y. So x1 plus x2 times y is x1y plus x2y, and trace is additive. So it's linear in each variable, that's clear. The important point is it is non-degenerate. This is a K bilinear form which is non-degenerate. So I don't know whether you have done this or etc. But you can take a guess. Even if you haven't done this, you can take a guess why this is true. Take a guess, and you must be right if you take a good guess. I am asserting that this is non-degenerate, and that is because of. Take a guess.
It's a field, right? So.
Yeah, but I mean, trace could be identically zero or because of some characteristic reasons, etc.
And the trace of 1 be 0.
Trace of 1 also can be 0, no? Suppose the characteristic is P and the L over K is degree P.
Oh.
The trace of 1 is 0. But you are right, we are not going to bother about such things in algebraic number theory. You are right. Trace is anyway non-degenerate because trace of 1 is non-zero. You are right. So the word is this. So this is why I said in field theory, I don't know how much you have done, but this is a characterization of finite separable extensions. You may have one definition, but a characterization of finite separable is same as saying trace bilinear form is non-degenerate. It's if and only if. So if you have a finite separable extension of, if you have an extension L over K, it is finite and separable if and only if the trace bilinear form is non-degenerate. So let's take that for granted. There must be an obvious easy proof. I don't remember.
So 1 minute. So if we just take y to be, trace of 1 will always be non-zero, right? Because the minimal polynomial of 1 is just x minus 1, right? Just 1, I mean x minus 1, right?
So, okay, no, sorry. Trace of 1, yeah, sorry, yeah. No, sorry. So maybe I myself confused while we were defining those coefficients, etc. That trace. So okay. So the definition of trace is sum of all Galois conjugates. See, trace is, yeah. So take back some extra things that I must have said at the time of coefficient of the minimal polynomial, etc. Those things are true only under nice conditions. Okay. Otherwise, the general definition of trace will be sum of all Galois conjugates. So if you take 1 as an element of L and L over K is a finite extension, then it has, suppose degree is n, then it has n Galois conjugates, right? So you have to take the sum of all that. That is the definition of trace. It is not the constant term. It is not the second term of the minimal polynomial. That coincides under nice conditions. Okay. So the definition of trace is sum of Galois conjugates. Definition of norm is product of Galois conjugates. So if you take 1, then 1 is treated as an element of L, and you have to apply sum of sigma of 1. But sigma of 1 is 1 because 1 is in K. So you'll be summing P times, and if P turns out to be the characteristic, then trace is 0. Okay. So this is the statement that we need, that finite separable is same as saying this trace bilinear form is non-degenerate. So recall that this is a characterization of L over K being finite separable. Okay, anyway, you have this bilinear form, and most of you would have thought this is anyway non-degenerate, and that's what I wanted. You know, the what is the word? The pathology of this not being non-degenerate is not of interest to us in number theory. Okay, so it doesn't matter. So what you naturally thought is correct for us. If you were doing field theory, then that was not quite correct, but for us it is correct. Okay, so because we are under nice setup. So I'm continuing the proof. I will start with, so once you have a vector space, once it is finite, many times we will fix a basis and work with a basis. So we will choose a basis of L over K. We will choose a basis of L over K and argue with that basis. But now remember the most important part of this proof. I'm going to argue with a chosen basis, but not just with that chosen basis. I will argue with one more basis. So you have, whenever you have a bilinear form, you have a notion of a dual basis with respect to that bilinear form. What should be the definition? Suppose you have a basis Vi, V1, V2, etc., Vn. And suppose you have a bilinear form B of V1, V, W. What should be the natural notion of a dual basis? The first guess must be correct. You take a guess, take a random guess. It will be correct, I'm sure.
I don't know. We can try to pick a basis such that the matrix of the bilinear form is nice, like it contains only diagonal entries, ones and minus.
Absolutely. The matrix is the identity matrix. So B of Vi, Wj is delta Ij.
Identity, I'm not sure.
No, I'm saying take that. These are
no, but it depends on the. We might not be able to find such a basis. No, it depends on the bilinear form.
Correct. Of course, it depends on the bilinear. Yeah. In general, it depends on the bilinear form. And in this case, you know, we are working with fields and the nicest bilinear form trace of xy. Okay, so see, what is dual basis usually? Isn't the following true if you have a vector space V over a field K and then you have V dual, right? Dual as space of linear forms, and then you have a dual basis, which is given in terms of Kronecker delta, right? Li at Vj is delta Ij. That's what I have in mind.
Okay.
But agree with respect to this bilinear form. So that would be the standard bilinear form. When I put it to this, you are right. So if the bilinear form is nice, you can take it to be identity. Okay, so in this case, I'm going to define it like that. So we'll choose a basis of L over K and argue with it and the dual basis. This is nice enough situation. And but anyway, I can define dual basis to be what I'm defining. No, if at all we need to bother what you said is correct or not, it's a question of does dual basis exist or not. I'm going to define my dual basis as Wj such that B of Vi, Wj is delta Ij. Okay, let me define that as a dual basis. Then you can ask the question, does it always exist? And then one will have to show that it does exist. Agree with this formulation? Was it Manav?
Yes.
Yeah. So let's continue. Are you saying something?
No, I was just saying yes.
Okay, fine. So we are going to define the dual basis as this one, that there is yeah. So I have the next slide. So the point of this slide is we are going to argue. So remember finally that we have introduced this particular bilinear form. We will argue with the basis. The basis will play a role, but its dual basis will also play a role. And you will see it's a very beautiful, ingenious proof. So let W1 etc. Wn be a basis of L over K. It's a finite extension, so it's a finite basis. My first claim is that, so where are these Wi's? W1 belongs where? In L. in L. My first claim is that without loss of generality, I can assume that these are integral over A. Do you see why this is true? So maybe I'll take 5 minutes extra because I would like to finish this proof. It's already 3:18, so I might take a few minutes extra. So do you see why, Nitesh, you can leave at the right time because you have another class. So why are these integral? Do you agree that if I take one element, I can make it integral by multiplying appropriately, like clearing the denominator, so to say? That's what we proved at the starting, no? If you have an algebraic element, then you can multiply it with a non-zero element from A so that it is integral. So for each of these wi's, you can get a non-zero Ci such that Ci wi is integral. But then you can take product of all these Ci's, call it C, and you can multiply by that C. So Cw1 is integral, Cw2 is integral, Cwn is integral. But then if W1 etc. Wn is a basis, then Cw1 etc. Cwn is also a basis. So you can assume that the basis is, all the elements of the basis are actually integral over A. So the reason is as follows. We have proved earlier that for each of the Wi, there is a corresponding Ci such that the product is integral. This Ci is from A. And you can take the product of the Ci's and multiply with that C. So you can take Cw. So C is product of integral elements. So C is integral. And Cw1 is integral, Cw2 is integral, Cwn is integral, and this is a basis. Because W1 etc. Wn is a basis. So without loss of generality, we are going to assume that your original basis, each element is integral over K. Each Wi is integral over K. Without loss of generality is explained by what you have done here. Okay, now we are going to take a dual basis under the trace bilinear. Yeah.
W2, okay, it was any basis, not a dual basis.
Say that again.
No, I was under the impression that W1 to Wn we are taken as a dual basis, but that is not the case.
No. This, see, dual basis makes sense only if you start with a basis, no. Otherwise, there is no dual basis. A dual
Your
base,
voice cut actually. What were you saying? Dual basis makes sense when?
dual basis makes sense only if you have a basis to start with, no. Dual basis meaning a basis which is dual to some basis, right? Only if you have a basis Vi, I can talk about a basis dual to that, no.
Oh, like, is that true for the thing which I was saying? What I was saying was that was different, right? That we can choose a basis such that the bilinear form becomes identity matrix. So
Oh, that's
there
what
we
you.
just have one basis. That
Okay,
is not related to
maybe
another.
maybe you know, you said something and I said yes, etc. And okay, so we were talking about two different things. Maybe they coincide under some particular thing. So by dual basis, I just mean the following. You give me a basis Vi, and I have the notion of a basis dual to that under the bilinear form. Okay, and the definition is simple. If Vi is the basis given to me, Wi is a dual basis if B of Vi comma Wj is delta Ij. That's the definition.
Okay.
Okay. Now it's another thing for us to, for me and for you to check whether what you have said coincides with this. Maybe under some nice conditions, but I don't know. So I also, you know, said yes, maybe without fully listening. Is it okay now?
Yes.
Okay, so W1 etc. Wn is any given basis, any basis. Okay, and without loss of generality, we are assuming that these basis vectors are integral. Now I am going to take a dual basis, the dual basis actually, the dual basis with respect to the trace bilinear form. So let this be the dual basis with respect to the trace bilinear form. What this means is trace of Wi prime Wj is delta Ij. This is the definition of dual basis with respect to a bilinear form. Agree? So we said that we are going to argue with a chosen basis and its dual basis. And one condition on the chosen basis is each of that is assumed to be integral. And now we will argue also with its dual basis. Dual basis just means this. Are you with me now? So let's continue. So what is the title here? Again, I said all my titles are for you to remember the proof much later. Okay, so this is a joke. There's a smiley here. It's just my way of remembering the slide. So let's continue. Let's be serious. So these Wi prime are where? These Wi prime are where? Where are these elements? They are in L, right? It's a basis for L over K. So they are in L. They are in L. Wi prime are in L. So these are in L. Nothing more you can say. As before, you can multiply appropriately and say that they are integral over A, no? You agree, right? If you have something in L, you can multiply by something from A and make it integral. And you can do this by taking that product, and you can take one C such that all these CWIs are integral over A. Same as before. One you can do, you will get CI. You take the product of CI, that will work, or LCM or whatever, that will work. So you can choose a C which is an element of A. If you recall our earlier proof, that C was chosen from A. You can always get an element of A such that all these are integral over A. CWI prime are integral over A. Okay. What do we have to show? Let's not forget what we need to show. What are we aiming at? The integral closure of A in L is finitely generated, and we said that we will only show integral closure of A in L is contained in what was the some finitely generated module. So I'm going to produce a finitely generated module over A such that the integral closure of A in L is contained in that. Okay, so we want to show that the integral closure of A in L is contained in some finitely generated A module. So how should we start? We should start with an arbitrary element of this set, right? So let Z be integral over A, and we have to exhibit a finitely generated A module containing Z. Then we are done. So that's what we will do. And so let Z be integral over A. Z is from L. So expand Z using your original basis Wi. So write Z as B1 W1 plus etc. Bn Wn. This is the original basis. W1 etc. Wn. The prime is the dual basis. Okay, so expand Z. Where will be the BIs? It's a basis of L over K. So BIs are from K. BIs are in K because it's a base of L over K. Okay. So now multiply with C. Take this C times Wi prime times Z. What can you say about this C times Wi prime Z? You know that C times Wi prime is integral. Z is given to be integral. Therefore, this product is integral. Product is integral. So all these are integral over A. Okay. Now, what do you know about coefficients of the minimal polynomial, etc.? If something is integral, then coefficients of minimal polynomial is integral. In particular, norm and trace are integral, and we are going to apply trace. So because these are integral, therefore, so also their trace. Trace of each of this element is integral. Agree? Because if something is integral, its trace is integral. Now, what is the trace of CWI prime Z? What is the trace of this?
Summation of CBI.
Yeah, I want an answer. See, Z is this. I want a number as
CBI.
CBI. That is why the title CBI. Okay, so remember this. So trace of CZW I prime is CBI. Okay, so this is clear because you are multiplying this by CW I prime. So CW I prime is multiplied every way. B comes out. So CW I prime WJ. And that traces delta ij. So only the ith thing will remain, and there you will get a 1. So bi will come out. So it is CBI. Okay. So where does this belong? So this is an element of L, and you are taking trace of that. So trace will be downstairs. So CBI is in K. CBI is in K, right? Because this is an element of L. These are integral over A, but these are elements.
C is in A, BI is in K, so CBI has to be in K, right?
CBI has to be in
K, because C is in A.
Correct.
C belongs to A, BI belongs to K.
That way also you can say. So BIs are in K and C is in A, which is in K. So CBI is in K. So where does this belong? The answer is K. So either like that, or this was in L, therefore trace of that is in K. Either way. Okay, so these are in K. Okay, so where does this belong? The answer is K. And so as I said, I'll take a few more minutes. Let's finish the proof. We're almost there. And I'll state one more theorem. That will be a good place to stop. So these are in K. And now I think maybe in the next line I am done. So this is the another thing that you should remember. These are in K, but we would like them to be in. Suppose I make this statement. We would like them to be in. We want something more, Then what will you fill it up with? These are known to be A. Yes, these are known to be in K, but we would like them to be in A, but that's not there. We don't have it. Unless we put one more condition. And what has
Why would we like them to be in A? Is that clear here?
No, that's not clear. I'm just getting responses from you so that, you will remember that we talked. That's the whole point. We want them to be in A will be clear in the next slide, because then I can produce. It's kind of clear, but not so clear. It will be clear, only when I state the thing. Now, since you have asked, I can explain why is it clear, but not so clear right now. The point is, we want to show that there is a finitely generated A module in which Z belongs. But Z is a linear combination of this. Now, if CBI belongs to A, then BI belongs to A by C, AC inverse. So you would have got Z as contained in AC inverse W1 plus AC inverse W2 plus etc. AC inverse Wn. But that's a finitely generated A module for that reason. Is that okay?
Yeah. That makes
Or was
sense.
it maybe one step before that I said that? Anyway, that's what we are going to do. We would like them to be A for that reason. But right now I did not mean that much. We would like them to be in A. See, suppose I start by saying that no, we would like to have something more. Then the natural answer is A. Only that I meant right now. Okay. So these are in K. We would like them to be in A, but that may not happen. But you can put one more condition so that it happens, and that is integrally closed. Assume A is integrally closed. Then you are okay, right? Because then CBI is integral over A and it belongs to K. So if you know that A is integrally closed, then CBI belongs to A. You agree? That's the definition of integrally closed. If you say that something is integrally closed, that means it's integrally closed in its quotient field. And CBI belongs to K on the one hand, and on the other hand, CBI are integral because trace of integral is integral. So this will belong to A if A is integrally closed. Therefore, assume A is integrally closed. So that's the title of this slide. Assume A is integrally closed. This is the second condition on A. What was the first condition on A? What was the first condition on A?
Noetherian.
Noetherian. So the theorem is, suppose you have a ring which is Noetherian and integrally closed. Suppose you have a ring meaning integral domain commutative with 1. Suppose you have a ring which is Noetherian and integrally closed, contained in some L. Take its integral closure in L. Then the integral closure is finitely generated as an A module. That is the result. Okay. So second condition comes here, and because of this, CBI belongs to A, and now you are done. Therefore, Z is linear combination of BI WI. This belongs to, so BI belongs to AC inverse, A by C. So this belongs to this, but this is a finitely generated A module. So Z belongs to a finitely generated A module, and therefore we are done. So we wanted to show this. And we took an arbitrary element Z from here, and we showed that Z belongs to some finitely generated A module. And the same finitely generated A module works for any Z, because your final answer does not depend on Z. Your final answer, that is also important. Okay, that's also important, that this final answer does not depend on Z. It depends on the basis that you have chosen, and it depends only on the C, but C did not depend on Z. C is before Z. C is right here. It does not depend on Z. So the same finitely generated A module works for any element from here, and therefore this is done. Okay, so this is the result. So what is the result once again? If you have a Noetherian integrally closed ring contained in a field L, then its algebraic closure, not algebraic closure, integral closure in L is finitely generated as an A module. This is what we have done. Okay, now let me leave as an exercise. So the exercise is this title. So can you just expand this title? What is UFD?
Unique factorization domain.
And what is IC?
Integrally closed.
Yeah. So what is the result? A unique factorization domain is automatically integrally closed. It's a very easy exercise. In fact, it's an exercise that you could have done in your school, because in your school, maybe I don't know which standard you would have proved it. 9th or 8th, maybe 8th standard maybe, or maybe even before, you have proved that there's a standard proof of root 2 is irrational. It's the same proof. UFD implies, I mean, it's the same trick. UFD implies integrally closed. So that you do. Otherwise, you look at Lang. Okay. Let me state the very first theorem of Lang's book. So Lang, if you look at the book, you will see that everything he calls a proposition or lemma. Very rarely he calls something a theorem. Okay. Especially in the first chapter, there are only 2 theorems, I think. So this is the very first thing stated as a theorem in Lang. So this is Lang's Theorem 1, and this is the result. A is a PID. A is a PID, and M is a finite separable extension of its quotient field. This is the hypothesis. This is the assumption of the theorem. So let A be a PID and let L be a finite separable extension of the quotient field of A. Then the integral closure of A in L is, would you like to guess the result? It's a very strong result, but from what we have proved and with the extra condition that it's a PID. So what can you say about a PID? Does PID satisfy both the assumptions of our previous result? The assumptions that we wanted for the finite generation result is what? We wanted Noetherian, but a PID is of course a Noetherian, and we want it to be integrally closed, but that also you know why. Why is a PID integrally closed?
PID is a UFD.
And exercise tells you UFD is integrally closed. So PID is a UFD and UFD. So both those conditions are true. Therefore, from what we have proved, what do we know? We know that the integral closure of A in LS as an A module,
Finitely generated.
finitely
As an A
generated.
module.
Finitely generated as an A module. Therefore, can you conclude something because it's a PID?
Free module.
Yeah, it's free. It will be free plus a torsion part, but there's no torsion because these are integral elements, so there will be no torsion. So you can easily check that. So it's a free module over A. But once something is a free module, there's a natural thing that you will ask, right? Suppose I tell you that I give you a vector space, and suppose I tell you that suppose I give you a vector space. Is there a natural question that you will ask me about that vector space? Suppose two of us are discussing.
Is it finite dimensional?
Is it finite dimensional? So answer is yes or no. Suppose the answer is yes. Will you ask one more question? There's automatically one more question that which you are forced to ask, which you are bound to ask. What is that?
I don't know. Do you have a basis of the vector space?
Say that again. No, about the dimension. See, suppose it's finite.
What is the dimension then?
What is the dimension? Of course, yeah. So here, what is the question that you will ask because it's a free module?
What is the dimension again?
Yeah, dimension. What is the word in module theory for dimension?
Rank.
Rank. Yeah, rank is the word used for dimension here. So what is the rank, and can you guess what the rank should be? In fact, it's clear from the previous proof, but even if you don't immediately remember the proof, Take a guess. What's the most natural number that you can think of from the slide? There is a most natural number on this slide. What is that?
Degree of L.
N.
Degree of L over K. Call the quotient field K, degree of L over K. And from the proof, it's clear, no, the rank will be that because it's exactly that W1, etc., Wn, which we use to generate. Yeah, of course, we said it is contained in, so you need a little bit more argument to show using PID, maybe a little bit more to show that it will be actually those things. So it is equal to. So free module over A of rank equal to degree of L over K. So this is the first theorem of Lang's book. Okay, if you have a PID, take its quotient field, take a finite separable extension, take the integral closure. It is a free module over A of rank, the correct rank, which is the degree of L over K. The integral closure is torsion free, that you can easily check. It's a small exercise, in fact, not even an exercise, it's obvious. And as an A module, therefore, so what is the proof? So finite. So what is the result that you are using in order to conclude it is free? Apply which result? Structure theorem for a finitely generated module over a PID. So PID is given to you, finitely generated, we proved in the last few slides, and therefore you can apply the structure theorem. It is also torsion free, therefore it will be free, and check that the rank is indeed L over K. It's a small check. So this is the last slide. Let's stop here. Sorry, I took a few minutes extra, but let's stop here. So I will stop sharing and I will also stop recording. Yeah, so if you have any questions, you can ask me. Otherwise, you can start leaving. I will leave at the end.